for those of you I haven't seen yet. My great pleasure to introduce Jong-Hyun Kim today. He's a research scientist at NVIDIA Research, working on really cool projects at the intersection of human perception, display engineering, and for applications in AR and VR. He did his undergraduate degree at Seoul National University with Professor Lee, so that's really one of the world's leading groups in object photonics, especially with applications to holography, near displays, and these computational displays. He's been with NVIDIA for a few years, and they had this killer paper at SIGGRAPH last year on foveated AR displays. So that really exploits this idea of putting variable resolution on the retina to kind of match what we can actually perceive and maximize the bandwidth of the human retina. And, so that was a really cool paper. I think he also has a demo of this project.
Yeah, it's demo of the prescription AR.
Oh, prescription AR. So they actually had a great paper at SIGGRAPH. They showed it live at the Emerging Technologies booth. There were a ton of people all the time, so you've probably seen this project. And I'm really looking forward to hearing more about this and a couple of other projects that Jong-Hyun is working on. He's now also visiting research scientist actually here at Stanford in my group. So if you want to chat with him, if you have any ideas, I mean, he's going to be around one day a week to hang out with us and work on really cool projects in the future.
Thank you. Thank you for the introduction. That was pretty much about the talk already. So I will introduce about our recent works about AR displays, especially two works, prescription AR and the foveated AR. And I'm working as a research scientist in NVIDIA Research. I'm also currently working as a visiting researcher in Gordon's lab. So the title is Towards AR for Humans. So our works actually were inspired by a human vision system. So let me start with the last year's AR display. These are the two AR displays released last year from the two biggest companies in the world. The left one is HoloLens 2. It's from Microsoft. It is the state-of-the-art AR display. It is still the most powerful wearable computer until now. However, many of you might not know about it, but Google still makes AR displays. They released Google Glass Enterprise Edition 2 in last year May, which uses the exact same optics of Google Glass 1, commercialized 8 years ago. So if you look into the specification, it is more interesting. HoloLens 2 has a 52-degree field of view, 2K resolution, and 566 grams. However, Google Glass Enterprise Edition 2 has only 360p resolution, 13-degree field of view, and it is only 46 grams. So it might be the last 360p resolution display in the world. These two AR displays, released in the same year, same target, from the biggest two companies, have so many different specs coming from the completely different approach. And I think this example clearly reflects the problem that AR display industry is facing right now. So HoloLens 2 is the highest performance AR display so far. However, Google Glass has been the smallest form factor AR display since 2012. But both of them are targeting enterprise market, so only used in the limited situations. So imagine that you're the head of the AR display team in Apple or Samsung, and you want to target for bigger market and bigger audience this year. Where do you want to target on this two-dimensional plane for your next year project? You might want to upgrade your performance, so going to the Y direction a little bit more, or you want to go X direction, so minimizing the form factor, or you just want to stay there because you think it is good enough and then reduce the cost. So I don't know the answer, but maybe our two recent works can be a clue for this question. The first one is called Foveated AR, which can elevate the performance using foveation. The other one is Prescription AR, a glasses form factor AR display which can replace your glasses. So Foveated AR is first AR display that actually can do the dynamically foveation is a glasses form factor. So the basic idea is to provide very high resolution image only for a small fovea region and a very large field of view but low resolution image for periphery. So let me start with the concept of foveation. So human eye is a really good camera. So the field of view is over 180 degree and the resolution can be up to 60 cycles per degree, which is 20 2010 vision. So to match the 2010 vision over the whole field of view, we need over 21K pixels for horizontal direction, which is not achievable with current technology. However, human vision has a very interesting visual acuity over field of view. The right graph shows the distribution of cone cells and rod cells in the retina. The cone cells, which is directly related to the resolution, are concentrated in the foveal region and rapidly decreased as it goes to the periphery. So you can know something in your peripheral vision, but you cannot read the detailed information. So therefore, in the single moment where user's gaze is at a certain direction, the user cannot perceive all the information at once, even if we can deliver this 21K pixels to the retina. So if we can track the user's gaze and somehow deliver the high resolution of the foveal inset display to the fovea by changing the optics, then we can reduce the number of required pixels a lot. And this is called foveated display. So some people, especially from the graphics or rendering community, ask me, like, why don't you just render a foveated contents on the normal display? Why do you want to make the system so complicated and move them around? However, foveated rendering without the foveated display is just half of the technology. Even if you are not using all the pixels at once, you still need to drive those 20K pixels somehow. And in the display maker's point of view, the foveated display can bypass all the complicated problems, such as transmission bandwidth and power consumption. So foveated rendering should be accomplished on the foveated display for the best efficiency. So this video shows the overall shape and the components of the Foveated Ar display. In foveal display, a full HD micro OLED is used. In peripheral display, HD laser projector is projected into the eye with the lens HOE, the holographic optical element. So let me start with the peripheral display beam path. The light rays from the laser projector meet the beam shaping convex lens and right angle prism and diffracted by this lens HOE and created a Maxwellian view display. Please note that this holographic optical elements, HOE, only reacts to the light from the laser projector and is transparent to the light from the outside. So this is the AR display. Since all the light rays go into the center of the pupil, the displayed image is all in focus. And for foveal display, so this shows the beam path of the foveal display. Light rays from the micro OLED located in front of the forehead is bounced at the half meter first, and then bounced again at the image combiner. It is curved image combiner, so it is magnified, and then delivered to the user's eye. It doesn't react with the lens HOE over there because it is lens HOE has angular selectivity. So it is just modified version of birdbath optics. And this shows the gaze tracking beam path. The IR LEDs located on the HOE frames shine some infrared lights to the pupil. Then the pupil image is reflected the other side of the half mirror and then goes into the eye tracker. So one nice thing here is that we can get a nice on-X eye image with this configuration, which has a better accuracy and robustness compared to the off-axis eye image. So based on the tracked gaze information, the micro OLED and the HOE are actuated simultaneously. So since the required traveling distance was different, we applied the double-threaded screw, as you can see, to move both of them correctly. So let me introduce the details one by one. So the peripheral display is a large field of view, all-in-focus virtual retinal display. We recorded on HOE with 3 color lasers, like the left figure, and reconstruct them with the laser projector, like the center figure. So it is phase conjugated recording system. The eye relief was only 22 millimeter, so we were able to achieve 85 by 78 field of view, which is over 100-degree diagonal. And resolution was low, but it was fine because it is for periphery. Since all the light rays are going to the center of the pupil, and also because the laser projector has a long depth of focus, the image was all in focus. However, the static eye box was really small, so it's around 0.5 millimeter. So you cannot see any image when you rotate your eyeball to somewhere else. But we solved this problem by actuating the hologram. So this is how we steer eye box. First, we projected the image larger than the HOV size. As eye rotates, we move the HOV to that direction and change the input image accordingly. So this dynamic eye box concept is presented here, but this is not the first dynamic eye box concept. So Changwon, who was my former coworker from SNU and also now working at Facebook, proposed a similar steering method by changing the effective light source position using a MEMS mirror. So, so his method is actually moving effective light source position with the MEMS mirror here, and this is our method that moves HOV. So, if we directly compare this HOV moving method and the this light source shifting method, it turned out that HOV shift method can provide much larger field of eye box at the given small eye relief and the large field of view. So in the right figure, especially for the small system, like when the eye relief is only 22 millimeter and the field of view was really large, then HOV shift method can achieve around 10 millimeter eye box. So if you have any questions, just let me know anytime. So foveal display is a modified bird bath optics. So the light rays from the micro display here is bounced from the half mirror and then bounced again at the image combiner. So we can design the various resolution of foveal display by changing the curvature of this image combiner and the location of this micro OLED. So we designed 30, 40, and 60 cycles per degree image combiner, which can provide 32, 24, and 16 horizontal degree field of view. We can also provide varifocal images by moving the micro display up and down a little bit, and we can move around this virtual image from infinity to very close distance. So Foveated Ar is composed of a varifocal foveal display and then all-in focus peripheral display. It was pretty reasonable choice because the depth information is mostly acquired from the fovea region. We also applied NVIDIA's deep learning-based gaze tracking algorithm for the on-axis gaze tracking. So there was a small kick in the image combiner, so I'd like to highlight this. So we embedded the half mirror image combiner inside the planar slab, like the right figure, rather than just coating the surface of the spherical mirror, spherical lens or spherical mirror. So this planar image combiner has a lot of advantages. First, it can achieve shorter focal length because of the refraction, as you can see here. So it is really helpful to make a very compact system. Second, we can avoid the ghost images. In the planar image combiner, there should be some minor reflections in the other surfaces, but it is not magnified. So compared to the spherical image combiner, because it is not magnified, it is blurred really well, so there's no ghost image. There's no ghost image. And last but not least, it looks better than the bug eye structure. So based on this design, we can satisfy the human visual acuity. This black line is the visual acuity for 20/20 vision over the angle from the fovea. As you can see, it is rapidly decreased as it reaches to the periphery. Our full HD foveal display can cover this red region based on the image combiner curvature. And our HD laser projector peripheral display can cover this blue region. So as you can see, without foveation, we need more than 20K pixels for 60 cycles per degree. But with foveation, we need only one 4K display for fovea and one for HD for periphery, and it is really enough. So we can minimize the required pixel numbers really a lot. Previous slide was for the center gaze, and this slide shows the gaze angle coverage. The left graph shows the required traveling distance for the micro OLED and HOV. To cover plus minus 20 degrees, micro OLED should travel 18 millimeter, and HOV should travel 6 millimeter. The required distance is different, but the ratio of them is consistent as 3:1. So we can actuate both of them with a single actuator. The right graph shows the angular resolution over gaze angle and eccentricity. So within the plus minus 20 degree gaze angle, the display provides foveated acuity. So many people ask me about the latency. So can you actually move the optics as fast as your eye? The answer is definitely no. But it can be also yes. The user eye just moves whatever they want to look, wherever they want to look, and it is really fast. However, when you change your gaze from this direction to this direction, your eye doesn't move slowly like this. It is moved like this, right? And this movement is called saccade. And when you saccade, your brain blocks the information for the very short amount of time because the information changes too fast. So if you look this graph, so this is contrast sensitivity over the time, and when you saccade, you became completely blind for this, like before and after saccade. So we have this 50 millisecond time slot that we can track the new eye position and move the optics accordingly. Since the required traveling distance for HOE was only 6 millimeter, the required speed of the motor is 120 millimeter per second, which is much slower than your eye speed. And in addition, both moving parts are super lightweight here. So micro OLED is only 3 grams, and HOE is just one film, so which makes it more practical. This is the benchtop prototype we made. The foveal display, it's really hard to see, but here's micro OLED, and you can move around with this linear stages here, and you can even move this direction, so you can move three-dimensional. And peripheral display, here's HOV here, laser projector is here, and this HOV is also actuated by these linear stages, and then you can move around in two-dimensional plane. All the results were actually captured by this 2 smartphone camera. As you can see, there are the real object here, and this strawberry and donut text is actually photo image, so it is augmented onto the real object. So before showing the result images a little more, I'd like to introduce how we calibrated foveal and peripheral display. For the geometric calibration, we captured the checkerboard images for all possible gaze angle and calculated the homography. So if it is, we want to show the left, this target image, like and if this is the foveal gaze center, fovea center, and this is the foveal region, then we first calculated this rectified target image with the first homography, and then calculate the real base image displayed in the laser projector and the micro OLED by calculating the second homography, which was captured from the checkerboard image. And also, the blending of the transition region is important. So when the resolution is changed very high foveal image to very low peripheral image at once, the transition region is very noticeable, and it is really bad for the display. So we applied this blending algorithm, which increased the blur size like this accordingly from foveal image to peripheral image, and then also blend the image by just changing the intensity over the eccentricity. So it really helped for the smooth transition. Finally, the color should be calibrated too. Since foveal and peripheral display had a really different color space, especially because of the HOE, we set the new color primaries for the overlapped region and calculate new color primaries accordingly. So the peripheral display has a much larger color space because it has more higher angular selectivity, but the foveal display is not. So we have to set these new color primaries and calculate the new base image for based on that. So let me show the display result. So we measure the angular resolution by calculating MTF with the slanted edge method. And as expected, the foveal display provides 30, 40, and 60 cycles per degree MTF 50 value based on the image combiners. And the peripheral display shows pretty lower MTF value at the center, but it was expected. This video shows how we can achieve very large field of view and a large eye box in the peripheral display. All the light rays from the laser projector is diffracted by this reflective HOE. And the field of view is so large, so we cannot directly capture it, so we capture the image from the top. The horizontal field of view can measure from the top was over 80-degree field of view. And as pupil is rotating from left to right, the holographic optical element was actuated accordingly. So if you think about the center, leftmost, rightmost holographic optical element position, we can achieve dynamic eye box for 12 millimeter while maintaining the eye relief, which was 22 millimeter, and field of view was all over 80 degree. So this is the result of the geometric calibration, blending, and the color calibration result. So you can see the foveal and peripheral region pretty well here. And before color calibration, so it is only geometric calibration was done, but the color calibration wasn't done, and there wasn't any blending algorithm here. So as you can see, the two different displays was so visible like this, but with the color calibration and the blending algorithm, you cannot see the difference. And we color calibrated for all color channels, so it wasn't easy and wasn't work for all HOE because HOE has some local defects, but at least theoretically it worked. So this is the video result for moving foveal inset. You can see that the high resolution inset is moving, and the real object here, 40 centimeter and 80 centimeter, is shown. So, but here the blending algorithm wasn't applied. But with the blending algorithm, as you can see, it is very much smoother, and it looks like a single display. This is the gaze angle coverage result. It is well calibrated from minus 20 degree to plus 20 degree, and because we calculate all the homography, the virtual image is actually bounded on the real scene, not moving according with the camera gaze angle. So this display also can provide focused cue. So by moving the foveal display, we can actually cover from 30 centimeter to 250 centimeter. And the required traveling distance was only a few millimeters because the magnification was pretty large. And when we changed we didn't change anything for the peripheral display rather than changing the image a little bit. And when the camera focus changing from 30 centimeter to 250, the peripheral blurriness wasn't changed that much. So it is all in focus display. So this is the full color result with defocus rendering. So this shows some kind of use cases. This is the strawberry and this is donut. And if you look strawberry, then the nutrition information of the strawberry was popped up. And as your gaze changed from here, to there, only high resolution part was provided by this Foveated Ar. So when you change your gaze from strawberry to donut, then you can actually read the donut intrusion, and the strawberry information was correctly blurred with the Foveated rendering software. So we also implemented a wearable prototype. So we 3D printed most of the parts and use a double threaded screw, as you can see. So the traveling distance of this micro OLED and the HOE was different, but it is set to 3:1. So this is the wearable prototype result. When the camera is at the right position, you can see the foveate image with the wearable prototype pretty well. So if you see the video once more, you can see the foveal display first because it has a larger eye box, and then if the camera is at the right position, you can see the peripheral image pretty well. So as a summary for Foveated Ar, this work is the first dynamically foveated AR display which matches human visual acuity in a pretty reasonable form factor. It provides 60 cycles per degree for fovea and 100-degree diagonal field of view for periphery and 12mm eye box. So this was the Foveated Ar. So back to this graph. So Foveated Ar was the highest performance AR display so far, which can meet the human perception limit, actually. So this is actually great. Then should we convince the decision maker to commercialize this Foveated Ar because it is so good, even better than the HoloLens 2? Let's say we can solve all those engineering challenges, including eye tracker, moving parts, and HOEs. Do you think people will buy this AR display and wear and use them around? I also don't know about the answer, but when I first developed the first version of Foveated Ar, I was able to do an internal demo. And this is me, and this is Jensen, who is our CEO. And during the demo, I got some lessons. So first, every facial structure is very unique. Second, 10mm image combiner is too thick. So this is what Jensen told me directly. He thinks putting something thicker than 10mm cannot be practical, which makes no sense. 3, many people even don't know their prescription, even Jensen. So we had to measure the prescription and locate the additional prescription lenses in front of the system, and it was quite a nightmare. So we built the world's first Foveated Ar display at the time, but half of them couldn't enjoy it without the prescription lenses, and some of them couldn't see it because their facial structure just didn't fit. So it raised me one question. So is it really possible to make the perfect AR display for everyone? So I mean, is it physically possible? So especially for prescription, at least 40% of whole population need an eyewear during everyday lives, and current AR displays cannot solve this problem. Sure.
Can I just ask one other question before we shift?
Sure.
The specification of 60 cycles per degree, that seems very high.
Yeah.
And for example, this display here, that's a very nice display, doesn't reach any very display. Would your problem be easier if you set the max at 10 cycles per degree, which is kind of more typical for the high quality display?
I mean,
10 to 15 is basically would things that become easier?
so this is probably full HD resolution, and you're sitting from there, and I believe it is more higher than 10 cycles per degree, I think. You don't think so? Yeah, but
But if we got it down for you so that it's a perfectly good display, was,
honestly, even the Google Glass right now, it's providing pretty high resolution. So making it larger field of view is actually the key. So if we can give up the field of view, and we can meet the higher, even 60 cycles per degree by just using a better pixel number thing. But we have to think about the field of view, and it should be optically. We cannot just achieve very large field of view by just changing the display. So honestly, 60 cycles per degree was an easy problem compared to like 20 cycles per degree, but larger field of view at the time.
I see. I thought you had 21K, but you needed to match 60 cycles per degree over a large field of view. So
Yeah.
the last put it was 12.
Yeah.
You're doing a favor of factor 5.
Yeah. The key was we cannot make a 180 degree field of view AR display with the current optics. So even though we lower down the the level, we cannot make it because there's no way to provide the large field of view display to the eye. Yeah. So we just wanted to kind of advertise our work is really, really good. So we just set the bar really high, and it was able to make a 60 cycles per degree display. But the key was actually the large field of view display. And it was the first kind of 100 degree diagonal field of view AR display. Okay. Okay. So back to the prescription AR. So especially for prescription, at least 40% of the population need an eyewear during everyday lives. And current AR displays cannot provide it. So AR display manufacturers now offer a flip-up visor design like a left. So this is HoloLens 2. So you can wear your glasses underneath. Or you can order another prescription lens set as Magic Leap does, which is another $300. So, but both of the approach actually increase the system size too much. So this glasses comparable design also affects the field of view and the eye box. So the additional space for the prescription lenses here, it actually increased the eye relief, and it actually decreased the field of view very much. And it also looks weird. It has some kind of center of the mass problem. And further, due to the large intraocular distance range, so some of them has a very short length between two eyes, and some of you has pretty long distance. The eye box required for the random viewer is actually much higher than the eye box required for a single viewer. So if we can make a customized AR display design for each prescription, for each person, we can actually bypass this kind of problem and then make the very small form factor system. So therefore, we propose the prescription embedded AR display. So the key of this design is actually using this main lens, which has a prescription in it, as a waveguide of the AR display. So this main lens can work as a prescription lens and also image combiner at the same time. So this is the video of the beam path of the prescription AR. So it is not visible very well, but here is this is the main lens. And the light rays from the micro OLED actually reflected by a beam shaping lens and goes into the incoupling prism and then bounces 2 times its total inter-refraction, and then outcoupled from this freeform image combiner. So so that is the beam path, and let me explain the design, how we designed the prescription AR. First, we have to set the curvature for each prescription. So we can actually calculate the curvature of the frontal and rear surface of this main lens based on the user's prescription, like normal glasses. The difference of the frontal and rear surfaces actually gives you the vision correction capability. So it's just it's like a just normal glasses store. But the important part here is we have to design everything else for AR display beam path. So we kind of parameterize everything you see here, like distance and all the angles and all the curvatures here, and even the materials. and we calculate everything at the same time in the ZMX by with this kind of physical constraint and merit function that we want to maximize the field of view, and we want to do the foveated optimization too, which I will explain later. So we calculated all those parameters at once for each prescription. So we have a range of the prescription AR set, but luckily human prescription has some range, and it is not that many. So we can offer all the people by just having a number of different designs. So we also applied foveation technique here. Usually when you optimize a lens, you want to optimize the lens like this red thing. So you want the lens work very perfectly for every instant angle. But because you know that this lens will be located in front of your eye, and you know the eye has a very interesting resolution limit, so we can optimize as blue line like this. So we can achieve very higher resolution for the center, but giving up a little resolution for this periphery. This one is fixed foveation. So if you rotate your eye, you will see very low resolution because there's no moving optics. But people tend to rotate their head rather than rotate their eye if it is very off axis. And perception scientists studied about that. And if it is over 15 degree, like 10 to 15 degree field of view, then people tend to rotate their head rather than rotating their eye. So with this design, we can achieve up to 30 cycles per degree at the center, and have a little more room here, so you can actually look around a little bit, and having a pretty good resolution over just uniform optimization method. So, so the prescription AR can cover all prescriptions which can be corrected by the current glasses, including myopia, hyperopia, astigmatism, and presbyopia too. So if we set the thicknesses and the front and rear surfaces, then we can calculate all the parameters like this. So if you bring this to, if you kind of bring this thing and make your own glasses, actually you can make your own prescription AR glasses. But the problem is that making the first mold is really expensive. So we made just one prescription AR prototype which has one diopter myopia. So I brought this so you can actually try that after. This is the manufacturing process is something like this. So we made this mold, and it has a two like front upper side and the lower side, and it is freeform image combiner. We coated. We make this and coated them accordingly, and then optically bond this, and then cut into whatever shape you want based on your frame design. So it is pretty much same as the current glasses technology. So the thickness, we set the thickness as a 5 millimeter. The resolution was 26 cycles per degree. It is limited by the this panel, not the optics, but it's pretty high. Field of view is 40 by 20, which is pretty comparable to the HoloLens 2. And eye box was 6 millimeter. It is a little low, but it was okay because we will change the frame design based on the user's IPD, and we will locate the display center to the user's eye. So actually 6 millimeter is pretty enough. We also have a varifocal capability, so if we move around this micro OLED a little bit, then you can cover from 50 centimeter to infinity. The weight was actually pretty good. The one that we brought here is only 45 grams, but it's a film type, but without the display. So normal weight of your glass is actually 30 to 40. So it is pretty, I would say this glasses form factor AR display. The transparency here is 70%, which is pretty high, and we can change the transparency by just changing the coating. So if you want to go outside, then you might need higher reflectance. So this is the display result without and with the prescription AR. So we mimic the one diopter myopia by setting the camera lens pretty close. So this is located 50 centimeter, 1 meter, and 3 meter. And as you can see, the myopic camera can see the closer objects really well, but cannot see the far object over there. But with the, we didn't change anything, but we just put the prescription AR onto the camera system. Then you can see that the focal plane is actually shifted because it has a light vision correcting for one diopter myopia. And you can see the pretty clear images, real object, which is located 3 meter. And then this NVIDIA part is virtual image, so augmented on top of the real images. So also, it has also focus Q capability, as I said. So we can move around micro OLED a little bit here, and then cover from 50 centimeter to infinity. The required traveling distance is actually less than 1 millimeter. So it's because this freeform image combiner has a very high magnification. So you can just move a little bit, then can cover the whole depth. And this is the experimental result for a varifocal experiment. And this is the AR display result with the rendered contents. So it is actually really good without prescription part. So it is well designed freeform image combiner AR display. But more importantly, we can solve the prescription problem too. Because this is the customized AR display, we can customize all the frames based on the user's facial structure. So similar to what you're doing in the glasses store, we can customize the glasses frame only for this user. So we 3D scan the facial structure with Kinect, and we parameterized all the frame designs with this IPD and everything. And then we do the minor correction, especially for the nose part, because everyone has very different noses. And we can 3D print it, and it was working pretty well. And one more thing which is very important in the real world AR social experience, but not that much recognized yet, is the transparency and the eye contact interaction. Because of the low efficiency and light leakage, you cannot see the user's eye from the outside with the current most of the AR display. So for example, HoloLens 2 here, it's a DOE-based one, Magic Leap also. They shine some very nice light, but you cannot see their eye. It's pretty interesting. But like birdbath optics like Nreal and Google Glass applied, it's more problematic because you cannot see their eyes, but you can actually see their contents. So you cannot see their eyes, but you should be able to see like what they're looking at right now. And Google Glass has the same problem, but because it is very small, it's kind of mounted inside the eyeball, and the depth is actually pretty actually behind the eye. It's like a TV from brain, so it's pretty awkward. But I mean, this is really important part of the daily AR display, but no one actually said this very well until now. So compared to those designs, this prescription AR has you can actually see the eye pretty well. It's mainly because this micro OLED, the light from the micro OLED is traveling inside the main lens, and some of them reflected to the eye, but the rest of them just travel more and then goes out this way. So you can actually, so right now the micro OLED is on here, but you cannot, you can see the user's eye, and if we block here with the frame, then you cannot see what the user is looking. So it can do the eye contact correction and also keep the privacy. So this is the wearable prototype that I brought today. So you can see the video here. So you can see the pretty clear image over there, and it is only 46 gram, I think. Yeah, it's on the scale, as you can see. So so returning to this graph, so Foveated Ar can meet the human perception limit, but it should be heavier than 300 grams. Prescription AR has a small form factor and pretty high performance. However, it is still a little bit heavier than the normal glasses. So back to the first question, if you are the decision maker, would you go for a 300 gram high performance computing device, or you want to go with something lighter? My conclusion was we have to make it even lighter, a little better than Google Glass 2, and include the prescription part. So until now, all the slides were my prediction and hope from the last year, actually. And now it is 2020, and there was a CES last week. And what happened at CES? So the keyword for AR display at this year's CES was the form factor, actually, which is pretty good. So everything is getting smaller, and several companies showed very different designs, but everything was tethered, actually. It is really interesting. So if you think about the previous standalone devices like HoloLens and Magic Leap, it is a little disappointing. However, they realized that it is impossible to make it small enough and attractive enough without cabling, because it's just impossible. So they gave up the untethered part and then decided to focus on the form factor. And field of view was quite just moderate, and they didn't even use DOE or HOE. Even Samsung used just simple glasses. I know they're doing something very crazy, like dynamic holography and everything, but they somehow use just simple bird breath optics. And I think we are at least going down the right way, at least. But they still couldn't solve the prescription problem yet. So these are the glasses from Nreal, which were the only demo that offered prescription set. But as you can see here, you have to make kind of wear another glasses in front of the real glasses. So the eye relief is very long. So it is like you're wearing glasses on top of your glasses, and it's actually pretty bad, I'll say. And they still have this privacy and eye contact problem too. So you can actually see what he's looking at, and the screen is located like behind his head, and it's really weird. So this year, I think we are going to the right direction at least, but I believe there should be another paradigm shift for AR display. So many people think AR as a transparent version of VR because AR has been recognized as the next version of VR, but AR is not a transparent VR. AR is not a flip-up visor or something you wear on top of your glasses. AR should be your smarter glasses itself. So if you think about everyday carrying items, the glasses are the most stupid thing around us. So everything around us is actively doing something useful, but this is just passive plastic device, and you spend like a few $100 every few years. So if you can make this one a little bit smarter, doesn't have to be like really smart, a little bit smarter, which correct your vision correctly and have a very nice form factor, people will happily upgrade their glasses to a new, smarter one. So in the future, you will go to the eye doctor to buy a new AR display. So then you bring the prescription to the glasses store, you choose your favorite frame, and wait for a few days, and there will be new smart glasses only for you. AR display will be the most fashionable electronic device in history. The world with only 3 or 4 different designs might be dystopian, actually. If you think about how many frame designs are in your local glasses store, you will realize that not customized AR display is not an option. So I believe these keywords will be more important for daily use AR display. Prescription, definitely. Customization. Privacy of both user and people around user. So people hate when we are taking video all the time in front of the eye, but to do the augmentation, we have to capture somehow. So it's pretty hard problem. Weight is also really important. At least, at most 100 gram, I would say. Then it should be tethered too. The transparency and the eye contact interaction is also very important. And finally, the vision enhancement. So not only correct your vision, but also kind of enhance your vision is really important. So that was my talk, and thank you very much.
Okay, we have a couple of minutes for questions.
What was the latency of following the
Maybe I should. So this one, so our latency limit was 120 millimeter per second, but definitely this stepper wasn't strong enough, so it's pretty low. But on the Benchtop prototype, we were able to achieve. It was actually faster than the requirement, so it was faster than 120 millimeter second. So the 120 was the requirement to follow your saccade. So the 120 millimeter per second was required speed for our system. So it can be converted to like angle per second. You can do the math, but
what is the number? What is the angle per second?
let me. Yeah. So saccade angular velocity is up to 500 degree per second, so it is super fast. But we have this 50 millisecond timeline for the engineering, and the required speed was so for 40 degree saccade, we need 6 millimeter traveling distance for the HOE, and it is, yeah, we should do that within 50 milliseconds, so it is 120 milliseconds. But definitely better tracker can reduce the time, because right now the tracking time is just constant, and if we can reduce the tracking time, and even if we can kind of estimate the new eye position by just looking at their first few frames, then we can do it much better. So there are different line of research for that, estimating the new gaze angle, gaze position.
Just following up on that question, I know that eye trackers that use cameras typically have a latency of a frame or two.
Mm-hmm.
And is that the type that you're using, or do you have a very fast analog tracking system that can?
In this system, we just use pupil labs, but we changed the software. So we captured just frame by frame, but I know it has some latency and it is pretty slow. But yeah, we worked for the high robustness eye tracking, so we changed the software a little bit, but we didn't use any special device for capturing. Yeah.
How did you choose the size of the gold the angular?
You mean the size of the micro OLED, or? So there's a trade-off between. So we can actually choose the highest resolution and the coverage. and like for the foveal display, so this graph here, the red graph, is a trade-off relation between the highest angular resolution and the coverage of the foveal display. And we had to use just existing Full HD micro OLED because we cannot make a micro OLED by ourselves. So it's just normal Full HD micro OLED from Imagine, and we designed all the optics for that. And we were able to achieve highest resolution, and it covers plus minus 8 degree. But for 30 seconds per degree, it covers plus minus 16 degree. Was it an answer? Good answer. Okay. Yeah. Yeah. Yes. Yeah, that's a really good question. Periphery is very sensitive to the luminance change, and it is actually, yeah, it was also our concern, and that's why I don't believe it can be commercialized like really soon, because the Maxwellian view display has those kind of problems always. So some of the AR display companies have actually commercialized the AR display with this kind of peripheral display, but yeah, everyone has that problem right now. So the display luminance was 200 nits, and the measured luminance at the pupil position was 40. So it's about 20%. Yeah. Oh. Yeah, it's a bird breath optics, so you can clearly see what your the user is looking at. So it has the same problem.
How the system judges actual distance?
Oh, that's a good question. So there are some studies that kind of estimating what the depth is by just capturing the eye positions. Yeah, convergence, but it has a lot of error because it's not very accurate, and the angle change is really small, and your eye jitters, so that a lot of problems. So what people, like including Gordon, is using is actually capturing the whole scene and track the gaze, and we know the gaze position, and then get the depth information of the outside by capturing the outside depths, using another depth camera for outside, and then move the image or changing the optics to that depth. So yeah, that's the problem, right?
So you can do the binocular tracking with the virtual, right? Or you have a depth camera and intersect the depth camera. I actually had a question on behalf of the students in the audience who are doing active research in this area. These are really well-engineered systems. What are some of the open questions here? Where do you think we could make some progress? What are some good research topics that are still open? So you didn't really talk about the limitations and potential future work.
Yeah. So for foveated display, I mean, this is we engineered really well, but everything should move around, right? So if we can do the dynamic foveation without actual moving part, that's a really good. I think that's a good topic, but I don't know. I have good answer for that now. And yeah, I think that's the open question for now.
Okay, great. So I think as usual we have a little reception back here with food and drink, so stick around for a little while. Jonghyun is going to stick around also a little bit. There's a demo there if you want to see the prescription AR. So if it's too packed there, come hang out with us here. We'll be around